Hello viewers, I am BSSP Rajasekhar, Assistant Professor of Mathematics, Government Degree College for Women, Nalgonda. In today's video, let us discuss about the change of basis. This is our class map. First, let us quickly recap some of the prerequisites for this concept. That is basis, coordinate systems, unique representation theorem, coordinates of x related to basis B, and coordinates of x related to standard basis. Let us quickly recap all those concepts, and later we move on to the concept of change of basis, and we discuss some of the applications of change of basis and why this is needed, and finally we solve some of the problems on change of basis. This is today's class map. Let us first recall our definition of basis. Let H be a subspace of a vector space V, an indexed set of vectors V is equal to set of B1, B2 and so on Bp in V is a basis for H if two properties. One, B is linearly independent set and B can span H. The subspace spanned by B coincides with H. That is, H is equal to spanning set of B1, B2 and so on Bp. If these two conditions are satisfied, then we say that B is a basis for the subspace H. If we can find a linearly independent set that can span the entire vector space V, then we can say that that set is the basis for the vector space V. So for a basis, we need two properties. One is linearly independence. So the vectors of that set must be linearly independent. And the second one is those vectors can able to span the entire vector space or subspace, as the case may be. So if these two properties are hold, then we can say that the set is a basis for that space. Whenever we can find a basis, then each vector x in V can be written as a linear combination of the vectors of the basis in a unique manner. Of course, for any vector space, there will be many bases. But for each fixed basis, any vector of the vector space x in V can be represented as a linear combination of the vectors of the basis in a unique manner. So those unique scalars or weights used in that linear combination are the coordinates of x with respect to B. So suppose B is equal to set of B1, B2 and so on Bn is a basis for the vector space V and x belongs to V. The coordinates of x relative to the basis B, or we can call them as B coordinates of x, are the weights C1, C2, Cn such that x is equal to C1 B1 plus C2 B2 plus 1 plus Cn Bn. And if these C1, C2 and so on Cn are B coordinates of x, then the vector in Rn xb is equal to a column vector with these scalars C1, C2 and so on Cn is the coordinate vector of x relative to B, or we can call them as B coordinate vector of x. We can call it as B coordinate vector of x. The mapping x to xb is the coordinate mapping determined by B. So for a standard basis, E is equal to E1, E2. If I take a 2 by 2 matrix, the standard basis is 1 0 and 0 1. So for example, if I take x is equal to 1 6, then this 1 6 can be written as 1 time 1 0 and 6 times 0 1. That is 1 e1 plus 6 e2. So here 1 and 6 are the coordinates. So the coordinate vector is 1 6. That is again x. So for any standard basis, the x itself is the coordinate vector with respect to standard basis. So xe is equal to x whenever e is a standard basis. So change of coordinate matrix, this is also seen earlier. Let pb is equal to b1, b2 and so on bn. Then the vector equation c1 b1 plus c2 b2 and so on cn bn is equivalent to x is equal to pb xb, where these b1 b2 bn are the vectors in the basis p. So those are column vectors. If we form a matrix using those column vectors, then that is denoted by pb. Then x is equal to pb xb. So we call pb is equal to matrix of b1 b2 and so on bn, the change of coordinate matrix from b to standard basis rn. And left multiplication of pb transforms the coordinate vector xb into x. Since the columns of pb forms a basis for rn, pb is invertible matrix by invertible matrix theorem. So x is equal to pb xb can be written as pb inverse x is equal to pb inverse pb xb, that is equal to ixb, that is nothing but xb, b coordinates of x. So we can conclude that pb inverse x is equal to xb. That is left multiplication of pb inverse converts x into its b coordinate vector xb. We have already solved many problems on this one. So these are the prerequisites for today's class, and the mapping from x to xb is a coordinate mapping. It's called a coordinate mapping, and it is a linear transformation which is 1 1 and onto also. So it is an isomorphism from V onto Rn. We have proved this in our previous classes, of course. So now the concept is, today's concept is change of basis. So whenever B is a basis of a vector space, any vector x in V can be represented in a unique manner. So the weights or scalars used in that linear combination are called coordinates. If we write it in a column vector or as a vector of Rn, that is denoted by b coordinates of x, where b is the basis. So sometimes we need to change that basis in the middle of the process. Then the coordinates will also change. If I used b as my initial basis, and after processing something at a later stage, another basis may be more convenient to solve the system. So then the same vector x is represented in another way. If I change the basis from b to c, then I need c coordinates of x. So in this topic, we are going to discuss about the process of changing such coordinates from b coordinates to how to change the b coordinates into c coordinates, and what is the advantage of that and how to do it. That is the present topic. So when a basis b is chosen for an n-dimensional vector space V, the associated coordinate mapping onto Rn provides a coordinate system for V. which we have seen so far. So V is a vector space with n dimensions. That means every basis of V contains exactly n vectors. Let B be one of such basis. So B also contains exactly n vectors. Then the mapping x to xb. xb denotes where xb denotes the b coordinates of x. The mapping x to xb is called coordinate mapping, and it is an isomorphism from V to Rn. That is, it is a linear transformation, and it is a 1-1 and onto also. Suppose that such a basis is chosen, then each x in V is identified uniquely by its B coordinate vector xb. By unique representation theorem, there will be only one such way. So those weights used in that linear combination of x can form the xb, B coordinate vector of x. In some applications, a problem is described initially using a basis B, but the problem solution is aided by changing B to a new basis C. Sometimes we need to change the basis for the convenience. Why? Let us see a little while later. Now, x in V is identified uniquely by its C coordinate vector xc. When the basis is changed to C, then x is represented by C coordinate vector xc. So in this topic we study how xc and xb are related for each x in V, and how to convert xb into xc, how to convert xc into xb. So what are the relations between these two? We discuss these topics. Let us visualize the problem. To visualize the problem, let us consider two coordinate systems. X is equal to 3b1 plus b2, using the basis b is equal to b1 b2, and where c is equal to c1 c2 is another basis. With that system, x is 6c1 plus 4c2, where these two are b1 b2 and c1 c2 are two different bases of a vector space V. Then xb, b coordinates of x are 3, 1. So the coefficients of these b1, b2 will become coordinates, and if the same are represented in a column vector, this is the coordinate vector xb. xb is 3, 1. And similarly xc is 6, 4. Since 6 and 4 are the coefficients of c1 and c2 respectively. So let us see these geometrically. Let us visualize this. So let this is my x, and these two are b1 is a vector and b2 is another vector. Both are in R2 space, of course. So let capital B is equal to b1 and b2. And since these two are linearly independent, that is, these two are in different directions, one is not a multiple of other, these two can form the entire space of R2. So now these two are my vectors in the basis. So using these two, I have to reach this x. So to reach here, b1 is multiplied with 3 times, with 3, so that I can reach here, and from this point I can use this b2. We know that in vectors, this vector is equivalent to this vector. Whenever the magnitude and direction are the same. So after reaching this 3b1, if I add this b2, I will reach x. So to reach x, I need 3 b1s and 1 b2. Since it is an indexed set, I need to maintain the order. So 3, 1. So my xb is column matrix 3, 1. Similarly, to reach the same x with another basis, here C1 and C2 are the vectors in a new basis C. So this is C1 and this is C2. These two are not multiples of each other. So these two vectors also linearly independent and hence can span entire R2. Now I have to reach this x, the same x, using these two new vectors C1 and C2. So to reach here, 6C1, if I multiply this C1 6 times with 6, I will reach here. And then I have to add this C1 4 times to reach here. So to reach x using C1 and C2, I need 6 C1s and 4 C2s. So 6 and 4 are the scalars used in this linear combination. So 6, 4, the column matrix 6, 4 is my xc here. So here the same x is being represented in two ways for two different bases. So same x is represented with 3, 1 with these measurements or with these vectors, and this same x is represented with 6, 4 with these two vectors. So while changing the basis, the coordinates will change like this, and we need to find the relation between these two. That is our task in this topic. Let us discuss some of the applications of basis change. Why we need to change the basis like this? It is very much used in image processing. For example, let us take the screen of this computer or screen of our mobile phone. There will be a resolution will be given there, 1328 into 1098 like that. That means there are so many 1328 rows and 1098 columns. So our screen is a combination of pixels. Each dot of our screen is called a pixel. So many pixels together form our screen. So each pixel have different colors and they use a color scale. Usually they use a gray scale 0 to 55. And to indicate the colors, we need to use 3 different colors. Those will be actually basis for the colors. Its dimension for the basis of colors is 3, of course. So you have to use those 3 colors. So each screen is a big matrix of numbers. when we are talking about a video, for a video content, we need at least 10 frames per second so that our eyes could not recognize the change. So if there are more than 10 photos are changed in a second, we can't recognize the change. So it will appear like a video to us. Otherwise, we can recognize the change. So at least we need 10 frames. For better clarity, we use 24, 30 frames, of course. So for a 1 second video, you need 10, at least 10, of course, at least 10 photographs with so many numbers. Each photograph has 1000 by 1000 at least, as per the resolution. So 1000 by 1000, so million into 10 million numbers. And each number is to be converted into binary system. So it will be usually 8-bit. So this large number of data, these large number of numbers of data is to be transmitted every second. So it is difficult sometimes to avoid the large data. There will be some image compressors, so that if standard basis is used for this, that is 1000, so then the vector will be r power n will be r power 1 million. That is a very huge number. We need to give numbers for each pixel. So if we change the basis using image compressors, the data will reduce so that the data can be transmitted easily. The popular JPEG, PNG, all such compressors will use these techniques. So further study of these basis change will do so many such applications. Suppose we need 3 colors in a color printer. We call red, blue, green as basic colors. So we may change those colors. With these 3 colors, we can produce any color with the proper combination. So if we can change the basic colors, any other, cyan, orange, blue. So the composition of a color will change. So the numbers, ultimately we give numbers. 3 numbers will form a different color. So what percentage of red, what percentage of green, what percent. Those are required. That's it. So we can change the basis in the middle also. So in this topic, we will know how to change the basis by using simple examples. Later, the same concept can be extended to any number of vectors easily. Let us look into it with the simple examples. Consider 2 bases, B is equal to B1, B2 and C is equal to C1, C2 for a vector space V, such that B1 is equal to 4 C1 plus C2 and B2 is equal to minus 6 C1 plus C2. Suppose x is equal to 3b1 plus b2, that is the coordinates of x with respect to basis b is equal to 3, 1. Find xc, c coordinates of x. So here xb is given, we need to find xc, and the relation between b1 and c1 is given here. And further it is given that b and c are two bases for the vector space. So given that x is equal to 3b1 plus b2, that implies we need to find xc. So c coordinates of x, that is equal to, x can be replaced with 3b1 plus b2. So we need to find c coordinates for this 3b1 plus b2. We know that the coordinate mapping is a linear transformation. It is 1, 1 and on 2. So let us use the property of linear transformation. So if T is a linear transformation, we have two properties. T of alpha plus beta is equal to T of alpha plus T of beta. And if C is a scalar, T of Cu is equal to C times T of U. Using those two properties, I can write this as 3b1c plus b2c. So using the first property, I can separate these two. T of u1 plus u2 is equal to T of u1 plus T of u2. Here my T is this coordinate mapping. Since coordinate mapping is a linear transformation, so we can write this vector equation as a matrix equation using the vectors in the linear combination as the columns of matrix. So this situation, this equation can be converted into a matrix form. So this can be written as b1c, b2c as columns of the matrix, and that should be multiplied by 3, 1, where 3, 1 are the coefficients of these two in the previous step. So if you multiply these two matrices, you will get again 3b1c plus b2c is equal to xc, which is our previous equation. So we know that b1c is equal to 4, 1, since b1 is given as 4c1 plus c2. So it is given that b1 is equal to 4c1 plus c2. So these two coefficients 4 and 1 will be the coordinates, and this will be the c coordinate vector of b1. Similarly, b2 is also given to us as minus 6c1 plus c2. So here minus 6 and 1 are the scalars used in this linear combination. So minus 6 and 1 are the coordinates, and these two can form a c coordinate vector for b2, which is represented by b2c. So our b2c, that is c coordinate vector of b2, is equal to minus 6, 1. So now I can replace this b1c and b2c with these values in this one, in the equation number 1. So from 1 I can write xc, that is c coordinate vector of x is equal to 4, 1, which is b1c, and minus 6, 1, which is b2c. These two are replaced with these two. and this matrix is multiplied with this 3 1. If you multiply these two, 4 into 3 12 minus 6 into 1 minus 6, so 12 minus 6, which is equal to 6. Similarly, 1 into 3 3, 1 into 1 is 1 plus 1, so it is 4. So xc is equal to 6 4. So these are my c coordinates of x. So c coordinates of x are 6 4, whereas b coordinates of x are given as 3 1. 3 1? Yes, 3 1 from this one. That is xb is 3 1. So in this we can observe that if we multiply xb with this matrix is nothing but b1c and b2c. So the vectors of the basis b are converted into c coordinates. So c coordinate vectors of the c coordinate vectors of the coordinates of the basis b are written here, are taken as this matrix. So if we multiply xb with this special matrix, we can get xc. Let us generalize this. Let us generalize this argument to have a, standard notations or symbols. So here we have taken only two vectors. So let us generalize this to n vectors. So let b is equal to b1, b2, and so on bn, and c is equal to c1, c2, and so on cn, be basis of a vector space B. We can say that from this statement we can say that V is an n-dimensional vector space. We can observe that the number of vectors in both the bases are equal. So if V is a vector space and it has some basis, then all other bases should also contain the same number of vectors which are present in a single basis. So here in both the bases there are n vectors. So dimension of V is n. Then there exists a unique n by n matrix P C from B. I will call it as C from B for convenience, such that xc is C coordinate vector of x is equal to P C from B xb. So this is our previous matrix that is being denoted by P C from B. So this matrix converts B coordinates into C coordinates. Instead of, observe here, instead of B to C, we are writing here C from B. The columns of P, C from B are the C coordinate vectors of the vectors in the basis B. You have seen in the previous example. So PC from B is nothing but the C coordinate vectors of the basis B. So we are taking the vectors of basis B and we are considering all the C coordinates of all the vectors, and each one will be a column of this matrix P C from B. That is, P C from B is equal to a matrix of B1C, this is the first column of this matrix. B2C, it will be the second column, and so on. B and C will be the nth column. So there will be n columns and n rows. It is n by n matrix. PC from B is the n by n matrix. So in the previous example, we have seen a 2 by 2 matrix. In the general form, it is n by n matrix. The matrix P C from B is called change of coordinate matrix from B to C. It is called as change of coordinate matrix from B to C. But let us call this as P C from B for our convenience. So it is easy to denote, easy to pronounce many times, easily. Actually, this is the change of coordinate matrix from basis B to basis C. So if you multiply this with XB, you will get XC. So this is the formula. This is the notation. This is the formula to change XB into XC. Here you can observe that B is adjacent to this XB and C is adjacent to XC. So it is easy to remember. XC is equal to PC from B. That is why we are writing B to C from B instead of B to C. PC from B XB equal to XC. This is the formula for us to change B coordinates into C coordinates. Multiplication by P C from B converts B coordinates into C coordinates. We have seen that already. The columns of P C from B are linearly independent since they are the coordinate vectors of linearly independent set B. Since the vectors of B are linearly independent, since it is a basis, the coordinate mapping is an isomorphism from B to Rn. So the vectors, the coordinate vectors of these linearly independent vectors will also be linearly independent. So the which are taken as columns of PC from B are also linearly independent. So see, these are linearly independent. PC from B is invertible. We have seen the invertible matrix theorem in the previous class. So all these statements are equivalent. Once all the columns are linearly independent, and there are n columns and n rows. So obviously each column and each row has a pivot. So PC from B is invertible. So if it is invertible, we can multiply this with the inverse of this one. So this is the relation which we have got in the previous slide. That is XC is equal to P C from B XB. I can multiply with the inverse of this on both sides. So PC from B inverse XC is equal to, and this is multiplied with its inverse. Then we get IXB is nothing but XB. So PC from B inverse XC is equal to XB. So this new matrix, the inverse of PC from B, converts C coordinates into B coordinates. So if xc is given, xb is to be determined, we can find this also. Or we can of course interchange b and c. That is simple. But theoretically, this converts c coordinates into b coordinates. That is, P C from B inverse is equal to P B from C. So this converts C coordinates into B coordinates. That is being denoted by us as per our previous notation. We can denote it by P B from C. Now C coordinates are converted into B coordinates. If we multiply with this P C from B whole inverse. That can be geometrically represented here. So this is our vector space V, and X is any vector in this vector space. And this is Rn, and this is also Rn. So using a basis B, B will also be here, of course. All the vectors of B and C will be here. But using those vectors in B, the unique representation, which is denoted by B vectors, B coordinate vectors of X, will be in Rn. So these will be the XB. And if we use another basis C, those C coordinates will be in Rn. So both of these will be different. This XB is different from XB, we have seen earlier. So the relation between these two is we need to multiply with PC from B. If you multiply XB with PC from B, you will get XC. If you multiply PB from C with XC, you will get XB. PB from C is nothing but PC from B whole inverse. So let us look into the change of basis in Rn, the standard basis, using standard basis. If B is equal to B1, B2, and so on Bn, and E is equal to E1, E2, and so on En, the standard basis in Rn, then B1E, that is E coordinates of B1 is equal to B1, B2E is equal to B2, and so on Bne is equal to Bn. So for a standard basis, both are same. Then P E from B is nothing but PB, which is equal to B1, B2, and so on Bn. So if all the vectors of the basis B are written in a matrix form, that will be the PB, and that will also PE from B also, where E is a standard basis. So let us look into a problem. Let B is equal to B1, B2, and C is equal to C1, C2 be basis for a vector space V, and suppose B1 is equal to 6C1 minus 2C2 and B2 is equal to 9C1 minus 4C2. Then find change of coordinate matrix from B to C and find XC for X is equal to minus 3B1 plus 2B2 using 48. So it is given that X is equal to minus 3B1 plus 2B2. So B coordinates of X is equal to minus 3, 2. Since minus 3 and 2 are the coefficients of B1 and B2 here. So XB is equal to minus 3, 2. and the C coordinates of B1 are 6 minus 2. Since B1 is given as 6C1 minus 2C2. So the coefficient 6 and minus 2 are the coordinates. So 6 and minus 2 form the coordinate vector, C coordinate vector of B1. Similarly, B2C, that is C coordinate vector of B2, is 9 minus 4. Since it is given that B2 is equal to 9C1 minus 4C2. So the coefficients are taken here, 9 and minus 4. So this is B1C and this is B2C. So change of coordinate matrix from B to C, which is denoted by P, C from D, is a matrix of B1C and B2C. These two are to be taken as columns of the matrix. So the matrix B1C is the first column and B2C is the second column for this matrix. So 6 minus 2, 9 minus 4. This matrix is the change of coordinate matrix from B to C, and it is denoted by PC from B. Now XC is equal to PC from B XB. So we need to multiply these two matrices. So PC from B is carried to here, and XB, which is given as minus 3, 2. So that is written here, that is carried to here. So you have to multiply these two. 6 into minus 3, minus 18 plus 18, 9 into 2, 18. So minus 2 times minus 3, that is 6. Minus 4 times 2, that is minus 8. So 0, minus 2. Minus 18 plus 18, 0 and minus 2. So this is the C coordinate vector of X. Let us go through some of the problems in the next video. I am concluding at this stage. Thank you for watching.